Okay. Make sure I have the good. Okay, hey everyone. Welcome to another lecture in MAE 113, Calculus for the Liberal Arts. So, today we're going to be doing the substitution rule. And we'll be following pretty closely what they've done in the class. Hello, Maple. All right. And if there's any questions, again, feel free to send something in the chat window along the side there. I'll try to keep an eye on it. It's a little hard because, again, I have the paper in front of me, and so I'll try to keep an eye on the chat window as well. And if you are able to answer the question for someone else, yeah, just send an answer back to them, or you can also use the @ symbol and then type kind of beginning of their username, and then it should autocomplete, and then you can actually kind of reply to them. Okay, so in the last two lectures, we learned how to handle integrals like this. We did something like the x to the, or the fourth root of x dx. We did something like we could integrate 1 over t cubed dt. And we could also integrate something like e to the x dx. So, but we can't use these same techniques on something more complicated. We can't do something like if we had the integral of 18x squared, and then we do all to the fourth root of 6x cubed plus 5 dx. So we can't really expand this out and collect like terms because of this fourth root's a little bit more difficult. When we're expanding stuff, we can do it with whole exponents, but we have this 1/4 here, and that's a little difficult. So what we need to do is we need to use our problem solving skills. And again, when we're at the beginning of the course, I talked about thinking backwards, starting with an answer and working backwards, like how we were doing the proof for the quadratic formula, drawing a diagram and writing out all the information that we know, finding patterns. But this one is reduce it to a simpler problem. And once we reduce it back to a simpler problem, hopefully it's a problem that we know how to solve. And that's what we're going to do. We're going to actually work with this example. So, I have 18x squared to the fourth root x cubed plus 5 dx. And you're like, oh, what the heck is, how can we make that simpler? What we do is we just replace it with, this is probably the most complex thing inside of these, this fourth root here. So we basically just do a change of variable, and that's what they call it, a change of variable, or we'll have a substitution. So what we'll do is we'll, instead of using x, we'll use u, and I'm just going to let u equal what's inside of that. Okay, so that means right now I have 18x squared to the 4th square root of u dx. Okay, so you might think I made it a little bit more messier, but at the moment we have two variables here. We have u and we have x. It'd be nice if somehow we could get rid of or change this 18x squared and this dx. So this is where the next part comes in. What we use is the differential. So what I do is I take the derivative. So basically on this side I have du, and then on this side I take the derivative here so that I have 18x squared plus 5, that's a constant, so that's 0, dx. And the idea is that if I integrated this, I get back to the original kind of original problem at the top there. So there's 6x cubed plus c. Okay. Now you're thinking, okay, I've written everything now. There's u and there's du. What can I do with this du? And what I do is I kind of look at this part right here. That is equal to du. Right? I could actually just kind of rewrite that here so that I have the integral. Here's 4u 18x squared dx, and that gets replaced with what we have for du. So that is just like that. Now that is something much simpler for us to solve. We know how to solve that. What we can do is just change that to u 1/4 du, and we use our power rule, and that power rule is that if I had u to the n du, that's equal to 1 over n plus 1 u n to the plus 1 plus a constant. And of course that's if u is that's only if n is not equal to minus 1, right? Otherwise we have a special rule for that. So we can actually apply that rule. So I get u, and this needs to go up by 1. So 1/4 plus 1 gives me 5/4, and plus constant, and I also have to have it over here. So what I get is 4/5 u to the 5/4 plus c. And okay, so we're almost finished, but we need to put everything back in its place. We've moved the furniture around a little bit. I've changed it from x to u, and now we need to go back to x. So basically we take that, we take this, and we put that in, so that my final answer becomes 4/5 6x cubed plus 5 to the 5/4 plus a constant. So we'll do a couple more examples of that, but what you'll find is that how am I picking something like u for this is I'm looking for something, this is quite the most complex part of it. I kind of look inside of this function and I set it to whatever's inside there. And I'm also looking for whatever I'm setting for u, if I take the derivative of it, does that clear up some of the crap that's hanging out outside here? And in this case, I picked a u in such a way that, yes, if I took the derivative of it, I was able to eliminate this 18x squared dx and was able to simplify it. So your choice of u will kind of depend on what the integration is, but basically you pick the hardest part and then see hopefully that the derivative cancels out some of this other stuff. Okay, so done that. I'm sure that I'll post this on the website. Scan those later. Okay, I'm just keeping an eye. So for those of you that are more mathematically interested in what I've done, this is what the substitution rule is. Basically, if I had I have a function inside of another function, and then I have its corresponding derivative also inside of it, what you do is you let that be u, and you let this be u prime, so that the integral is fu du. But, you know, there's no point in memorizing this. It's just explaining what I'm doing, but really I think more examples will kind of get you that intuitive feel for what the substitution is. Again, it's just replacing complex parts inside of these integrals and hopefully making the problem a little bit easier for us to solve. So here's another example. If I had 2x times x squared plus 3 to the 4th dx. So what would I do? You know, this isn't very difficult. Here, this to the 4th part is kind of the harder part, and kind of look inside of this, and I'll make this, so let u equal x squared plus 3. Okay, so if I do that, what I get is the integral of dx u to the 4th dx. And I still have the 2x and the dx here, so differentiating it, what I get is 2x. The 3 is a constant, so that's the derivative of that is 0. And then dx. And again, if I integrated at both sides, I get back to the original u. And that is what I have right here. This du right here. I have this 2x. It's right here. So that's what I can do. I can replace that 2x dx with the du. So I'm left with u to the 4th du. And again, this is very straightforward. This is using our power rule. So the exponent goes up by 1, and we take that 5th and put that into the denominator. Don't forget our constant of integration. And then, because we've done an change of variable to u, we have to put it back to x. And what did we have originally for our u was x squared plus 3. So our final answer becomes 1/5 x squared plus 3 to the 5th plus the constant. Okay. Was there another way of doing this? Yes. Yes, there was. Could I have done this without the substitution rule? Yes, you could have. So there's kind of like the first way. Here's the second way, which is not how I would want to do it. You take this. I'm going to also call it the hard way. To the 4th dx. And yeah, you could expand and simplify that. I just went to Wolfram Alpha, and it expanded this for me so that I got 2x to the 9th plus 24x to the 7th plus 108x to the 5th plus 2/16 x to the 3rd plus 162x dx. And then we can, using our original rules, there's my property 1 that I'm using. 24 x to the 7th dx plus 108 x to the 5th dx plus 2/16 x to the 3rd dx. Probably the hardest part would be expanding that all out. These are quite simple to integrate, so that in the end what you should get is 1/5 x to the 10th plus 3x to the 8th plus 18x to the 16th plus c. So that's all I did. The hard way is expand that. Expanding out those terms and then using our other rules. Okay. So what other problems could I come up with where expanding it probably wouldn't have been able to? Here's another one. Let's use, here's 3. So here is an example. Let's do, we're going to evaluate x over 3x squared plus 1 dx. Okay, so probably the most complex, or the more complicated part of this is what's in this denominator here. So what I'll do is let that be equal to u. And then if I took the derivative of that, what do I get? I get 6x dx. Again, the plus 1 is a constant, so I just ignore that. And let me just rearrange that so that I bring this 6 over. So I get 1 over 6 du x dx. So what I can do, I actually have done that. What I have is, here's my u, I covered that part. And now I still am left with this x dx here. And that's right here. Here's our x dx. And that is equal to 1/6 du. So I can rewrite that. I'm going to just split this up to show it a little better. So I have 1 over 3x squared plus 1, and then I have x dx. I'm just splitting these two. I can perfectly do that. That's okay. But that way I can show you what I'm doing a little bit more clear, so that when I do my substitution, there's my u right there, and then I have my x dx, and that's equal to 1/6 du. We don't have to worry too much about this 1/6 because I can just pull that out front. That's one of our properties of the integral, and I can substitute that in so that I get, so it's 1/6, and now I can take the integral of that, and that is 1 over u is ln u plus the constant. And we're almost done. We have to put back our variables the way that we found them. So the u we substitute back in. So I got ln 3x squared plus 1 plus a constant. Notice that I don't need to have the absolute bars because 3x squared plus 1 is greater than 0 for all x in the reals. So I don't have to worry about the absolute bars. And there's my answer. So I was able to evaluate that. Okay. What's another one? Here's my integral. And again, we're going to evaluate this. So evaluate. And we're going to do the natural log of x. We're going to cube that, and then we're going to divide by 2x dx. And what's the most complex part of this integral is probably that ln x inside of that cubed. So what I'll do, I'll let u equal that ln x. And then if I take the derivative of that, the derivative of ln x is 1 over x dx. So, let me just have a couple things. I have this ln x cubed. I have the 1/2. I have the 1 over x dx. So, this part here, that's equal to du. And then this part here, that's equal to 3 cubed. And you might start panicking, oh no, what do I do with this 1/2? Don't worry about that. We can pull that out in front of the integral so that I'm left with ln x cubed. I have 1 over x dx, and so I'll just do my substitution now. So I got the 1/2, the integral of u cubed, and that is equal to just du. So I got the 1/2. And now I integrate this, so it goes up by 1, and that also goes down into the denominator, plus c. So I have 2 times 4, that's 8, u to the 4th, plus c. And we need to put our variables back where we found them. So I got 1/8. And we put the u back in. So that is ln x to the 4th plus a constant. Okay, any questions about that so far? Hopefully everyone can hear me okay. Hopefully it's clear. The chat's really quiet. So that's my third sheet. Okay. So again, all we're doing right now is we're using the same techniques that we've learned previously. All we're doing is changing the variable so that we can make it a little bit easier for us to apply the rules that we already know. Let's do a exercise out of the textbook. This is 57 out of the section, I think it's 6.2, and that's on the substitution rule in Tan's calculus textbook. Excellent, thanks. I'm just looking in the chat. Thanks, Adams. And perfect. So let's do 57. So what they are doing is, let me write that out. So they have a rate of change. Again, as soon as you see rate of change, you immediately start thinking derivative, derivative, derivative. So the rate of change of the unit price, P, and this is in money, in dollars, and we'll call it swoosh shoes. They're a knockoff of a particular brand that I was thinking of, so given by, so someone came up with this function. They said that the rate of change of the unit price is equal to minus 250 x all over 16 plus x squared all to the 3/2, and the x is the quantity demanded. And daily in units of 100. And now if you can't read my writing, it's also in the textbook, so I'm just kind of writing out important stuff. Then the next part, it tells me to find the demand function. And they're for these shoes, And they also give us some information, like some additional information. This interesting little tidbit: if the demand quantity daily is 300, when the price is $50 a pair. Okay, so what they're telling us is, here's the rate of change of the unit price. This is P, and the demand function, I should probably write some switch. What this is telling us is they want us to find p of x. So they basically want us to integrate that. And of course, as soon as you need to integrate it, you're going to have a constant of integration, which means that you need some additional information to figure out what that constant is. And this is what they tell us right here. The demand quantity, which is p of x, when x is equal to 3, the price is $50 a pair. So what this is telling us right here, that p of 3 equals 50. So basically what they are wanting us to do here is an initial value problem, which we did, I think, in last lecture. So this is, we've reduced it back down to an initial value problem. So what is our attack? We have to integrate p of x to get use p of 3 equals 50 to get the constant of integration. And that's an ugly derivative that we're going to have to integrate, but of course we're going to use what we learned today to integrate that. So what I need to do is integrate that. So we do the integral of, so this is going to be p of x is equal to the integral of the derivative. So again, what we're doing is essentially undoing the derivative. You can think of the derivative or the integral as the inverse operation of the derivative. So I'm just rewriting what we have up here. Move that down just a touch. There we go. Maybe let's use red. So what I kind of look at is, yeah, this is kind of gross. This is grosser. So you will set this part right here to be our u. So that's 16 plus x squared, just that. And then if I take the derivative of that, I get 2x dx. I mean, I have the 250 there, but let's pull that out first. So I'm going to take out this minus 250 right on the front here. So now I'm left with, I'm going to leave this x dx and 1 over 16 plus x squared to the 3/2. Okay, so I can replace the u, I can replace this for u right there, and I don't quite have x dx. I have 2x dx, but that's okay. We can actually pull, just kind of rearrange that, so I got 1/2 du is equal to x dx. So that's okay. So now I've got something that I can rewrite that with. So I got minus 250 and I have 1 over, and now I substitute in the u, so that is u 3/2. The x dx is equal to 1/2 du. Okay, and that's just a constant here, so I can actually pull that out. So I get minus 250 times the 1/2, and I have the integral of 1 over u 3/2 du. Okay, and again, that's easy to integrate now. So I have the minus 250 over 2, and I'll rewrite this. So I got u to the minus 3/2 du. I'm going to leave that at the moment. There we go. So you have 3/2, negative 3/2 plus 1. So that gives you still a minus 1 over 2. So I get u to the minus 1/2. And I can't forget what I have in the bottom here. So that's 1 over gotta make sure I have a negative 1/2. So that is equal to minus 2. Okay. So immediately I can cancel out these 2's. I have positive, negative and a negative, so that becomes a positive. So I'm left with 250 u to the minus 1/2 plus c. And then I can substitute in what that u was, which was 16 plus x squared. And I have the minus, so I'm going to have 250 over the square root of 16 plus x squared plus a constant. There's page 4. So I can continue on to the next page. Here's the 5th. Okay. So we did number 1. We integrated it to get p of x. So then the next thing I need to do is figure out what that constant of integration is. So we have to use that information that p of 3 is equal to 50. So now we substitute that in. So p is equal to 50, 250 over the square root of 16 plus, and then the x in this case is the 3, so 3 squared plus c. So I get 50 is equal to 250 over 16 plus 9 plus c. 16 plus 9 is equal to 25. So it's the square root of 25 plus c. 50 over 250 over 5 plus c. And what I get is 250 over 5. Our 25 divided by 5 gives you 5 plus the 0. And then 50 minus 50 equals c. So therefore c equals 0. And so therefore our final demand function is p of x is equal to the 250 over the square root of 16 plus x squared plus our constant, which is c, and I won't bother writing that out. So there is our final answer for that. You lost me with all the math on this side back there, maybe? Okay, sure. Yes, we can talk about that later. I'm just not sure at which part. Probably the more, just around here is probably what I was doing, was just trying to figure out how I'm adding plus 1 to minus 3 halves. And then kind of dealing with a fraction when I have to do my 1 over n plus 1 kind of part here. But yes, we can definitely talk about that. We can talk about that later. Okay, so that is all that I have for today. I hope that was fairly clear and straightforward. But again, while there is kind of that rule, the substitution rule here, which you'll probably find in the textbook, it all comes down to finding things that are pretty complicated, just replacing it with a variable, and hopefully it simplifies it down to something that we know how to solve. And from there we can integrate that and then replace it back in by changing it back from our variable. So in this case we're changing it back from u to x, and there is our final answer. Okay. So the question, yes. So let's do that a little slower. We can redo that. I'll do that a little slower. Okay. So let's look at doing the integral of 1 over u 3 halves du. Okay, let's do that. Perfect. So our rule is, and what we're going to do is we'll have to u to the minus 3 halves du. So again, the rule for us is u to the n du is equal to 1 over n plus 1 u to the n plus 1 plus a constant. So that means if I apply the rule, I have my u, and so it needs to go up by 1. So I take the 3 halves plus 1. I have my constant here in front, but I also have to do the 1 over n plus 1. So that's the same as this over here. So I have 1 over minus 3 halves plus 1. Okay, so to figure this out, the minus 3 halves plus 1, that's equal to, I have to find a common denominator, so that the 1 becomes 2 over 2. Minus 3 plus 2, that becomes minus 1 over 2. So that exponent here simplifies to u to the minus half plus a constant. And then same thing here, it's 1 over minus 1 half. Now, I have 1 over minus 1/2. I usually just flip it up so that it becomes minus 2. The other way to look at that is that you could rewrite that as minus 1 times 2 to the minus 1. And then, again, we can, when you have a negative exponent, by moving it up, we can eliminate that so that I have the minus 1 still down here. And if I move it up, it becomes positive. So that is equal to 2 over minus 1, or that's equal to minus 2. So 1 over minus 1/2 is equal to minus 2 u to the minus 1/2 plus a constant. And so we've integrated that. And which page is that? Go back to the original. That's what we did here. So I integrated it. There's the u to the minus 3/2, which is right there. And we worked it out so that we got the minus 2u to the minus 1/2 plus a constant. Why is there a plus there? Well, there was a minus here. So we had a minus and we had a minus, and this turned into a positive. So, and then we continued to simplify this. The 2's canceled with each other, so that I was just left with the 250 u to the minus 1/2 plus c. And this is a square root. There's a negative, which means that it must go into the denominator, and so I'm left with the 250 over the square root of 16 plus x squared plus a constant. I hope that answered the question. Is that okay? Good. Okay, perfect. If you guys have any more questions, feel free to send me an email, or if it gets really complex, send me like what the question is. Take a picture with it with your phone. Make sure that it's clear enough that I can read it and I can try to figure it out, and then I'll write out something and scan it back, or we can talk on the phone or whatever. We got lots of time. And what I would suggest is going to the section in the textbook and just kind of starting out a couple of those exercises. But let me just go grab the textbook. I'll be right back. Let me go. So, I'm back. Okay, so this is section 6.2, the integration by substitution. So, pick problems. Let me just straighten that out. Pick some problems again. Working through these, and I can set an assignment, but really it's just picking questions that you think that will help you. Start out with an easy one. Number 1. Integrate that, and you'll have to use the substitution. And do that. You should be able to do that. Maybe I'll use a piece of paper here. You know, this is exactly how I used to do it when I was learning calculus. You just kind of just sit there and practice. Okay. And right in here looks to be the more complex part. So again, let that equal u. Yep. So immediately what I can do is I'll just rewrite this for dx. And so what you see here, there's the du, there's the u. So if you integrate that, you get u to the fourth du. We know how to integrate that. It goes up by 1, and the fifth also goes into the denominator plus a constant. Remember to put our u back in so that you get 4x plus 3 to the fifth plus a constant. So again, just go through and find things. Here I would probably set that to u. That's a little bit harder, but I would probably pick something like this right here. There's the squared. So I would probably set that equal to the u in this case right here. So let that u equal x cubed minus the 2x. And if I differentiate that, get 3x squared minus 2. And what a coincidence. There it is right there. So I can't write in the book. It's already here. Right there is my du. And I've got the squared here. And inside there is my u. So I have u squared du. And we can integrate that, replace our variable, and you're done. So again, probably if there's some sort of, you're cubing it or you're squaring it, or it's inside of a square root, probably whatever is inside of it, let that equal u. And then hopefully, if you take the derivative of that, that derivative is somewhere on the outside of that function. So in this, you take the derivative of du x squared, that equals 4x, and there it is right there. If I take the derivative here, x cubed plus 2x, that's equal to 3x squared plus 2, and boom, it's right there as well. So you're always looking for a u where the derivative will help you kind of, the derivative is there. And that's all there is to it. Okay, again, I hope this has been working out for you well. I will post the lecture notes. I'll scan these and post them on my website so you can check it out. It's cohar.ca, and under the header menu you can click courses, and then under that it's MAE 113. You can click that, and on that page has all the links to the videos and the assignments. And as for the tests, they are marked. I just have to figure out a way to scan all of them and send them out to you. So, and probably we'll go through the test. Again, they're interesting problems that you should know and have mastered, and we'll go through that. I'm not sure if it may be the next lecture. on Thursday, but yes. We're going to continue doing the live streaming for as long as I can, assuming that the internet is going to stay up, that YouTube is not going to crash, and so we are looking for. Sorry, I was mumbling. I was mumbling. I just saw the chat. So we're looking for a u value where the du is equal to u prime. Yes. Yeah. It helps us to eliminate some of the crap in the integral. So again, we're trying to simplify it as much as we can and revert back to the rules that we already know. Indeed. Okay. I hope you enjoy the rest of your afternoon and practice a couple of those. Pick and choose what you like. But yeah, these all look good all through from 1 to 50. Pick any of them and try them. Check the back of the book. Are you getting the answer? Are you not? And if you are having more difficulty, just send me an email with the question or the problem, and I'll write out a solution for you. Okay, take care. Do, 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 do.